Okay, so let's wrap up chapter 5. Section 5.3, it also talks about mathematical writing. Some of the, I'd like to just mention some of the highlights from this section. I hope you had a chance to read it. If you haven't, I highly recommend reading it. Just some common conventions that we use when we write proofs. One, for example, never begin a sentence with a mathematical symbol. Okay, we talked. I think I briefly mentioned this last week. If you want to use x, like x is an integer, don't start the sentence with x as an integer because it would look like a lowercase x. And especially if you typed it up, Microsoft Word or something might capitalize that x, and that would have a different connotation. We would capital letters are usually sets. So try not to use a math symbol to start a sentence. And then use I mentioned this when we first started writing proofs. Just use regular grammar. Like if you start it with each sentence with a capital letter, you end each sentence with a period, and you can. Oftentimes we write one sentence on each line, which is fine, but if it makes sense, you can just kind of wrap it around like a paragraph. But some other things, avoid misuse of symbols. If you want to say two sets are equal, don't say set A equals set B. I mean, so kind of using the symbol to kind of make a shorthand. I mean,
could you say that set A is a subset of set B?
Well, what I would say, you could say something like this: for sets A and B, A equals B. And so that way, if you haven't already told the author or told the reader that A and B are sets, this is kind of a bad use of the equal sign. Just use the word equals. Okay, you just say the set A equals the set B. I mean that would be better. But that's an example of like a misuse of symbols. Okay. May have some other examples here, but those are. Avoid using unnecessary symbols. If you don't need a symbol, you don't have to say every integer x is either even or odd. The letter x has no real purpose in that sentence. You just say every integer is either even or odd. Okay, so don't use unnecessary symbols. Number 6 says in this 6th point in here says use the first person plural. Oftentimes we use the word we when we write math proofs. It's kind of like the reader should be joining you in kind of this conversation about the proof. Like you're trying to convince this person. You kind of keep in mind that somebody else should be reading this. So it's just we use we or us rather than I or you. Now, so this one kind of really resounds with me because when I wrote my doctoral dissertation, my father he writes a newsletter on commodities markets, and so he's like a professional writer, and so I was like, Dad, here, proofread. You want to proofread my dissertation? Well, he went through, and as if it was like a scientific journal, where a scientific journal is always in like third person, like the researcher found that this, and that's like third person, or it's like passive voice, or it was found that. Blah, 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 blah. And so everywhere I use the word we, like in my dissertation, he marked it out and put it in this passive form. And then he hands it out. He's like, oh, there's errors all over this. And I'm just like, Dad, that's not very helpful because that's not the style. I mean, it's just a different style. Mathematical writing, it's very common to use this. I mean, it's pretty much everywhere. We use we instead of it was shown by the author or by the investigator, or it's just a different style than like a scientific journal or something. What else? Yeah, I mean, I think there's a lot of good. I don't have to read the whole section to you, but those are some ones I mentioned. And they give you a sentence that's a common kind of misuse of phrases or terminology or symbols, and then they give you how you might correct it. Okay, and this is where once you start reading more proofs, all these things just kind of come to you. I mean, you don't really have to think about it. The different conventions, it'll just start sounding better to you to use one phrase than another. Okay. So, any questions about that? So that's all I wanted to say. So then let's just talk about let's start chapter 6. So this is a new proof technique. So we've done direct proofs of if-then statements. We've done proof by cases, proofs by contrapositive. So proof by contrapositive is the first kind of example of an indirect proof where you're not actually proving the statement, you're proving something equivalent to the statement. So proof by contradiction is more like that. It's not a it's another kind of indirect way to get to the statement you want.
So kind of like hearing a direct proof just instead of proving it's true, you're proving it's false.
Well, it might seem kind of odd at first, or kind of just a fuzzy logic, but what we're going to do, when you start with a statement that you want to prove is true, often it might be hard to just go directly, prove a direct proof of this statement. So the proof by contradiction, we'll see you actually start off assuming that the statement you want to prove is false. And then we'll show that if it was false, then then that produces some kind of nonsense. Like, well, if I assume that it was false, then this is true, but that can't be true. It's nonsense. It's a contradiction. So our original assumption must have been wrong. Okay. So that's what we'll talk about, and I'll show you hopefully a couple of real classic proofs that are proven by proof by contradiction today. So this concept of proof by contradiction has been around for thousands of years. I'll show you an example. So even the ancient Greeks knew that there were infinitely many primes, and I'll show you a proof today that's pretty much equivalent to Euclid's proof of that there's infinite many primes. So let's start chapter 6, proof by contradiction. Okay. So oftentimes the statements that we've proven some are conditional statements, if P then Q, but you can actually use proof by contradiction to prove any type of statement. Okay. So proof by contradiction can be used to prove any form of let's say prove a statement of any form. Not just conditional. Statement. Okay. So that kind of becomes one clue. If you're given a statement to prove and it's not a if P then Q, then you might look to a technique like proof by contradiction. So the statement, there are infinitely many primes. There are infinitely many prime numbers. That's a true statement, and that's not an if-then statement. Right? There are infinitely many primes. So I mean, how would you? I mean, you prove by contrapositive. It's not an if-then statement. So we'll use proof by contradiction to get a statement like that. Okay. So recall, a contradiction is a statement that's always false. Okay. A contradiction is a statement that's always false. Okay. The author, I think does a good job of explaining the symbolic logic behind this proof technique. I mean, he talks about a lot of times about the statement that one statement that's clearly a contradiction is the statement P and not P. So this is, I think, the example I gave you when I said a contradiction. I mean, how can P be true and the negation of P be true? It can never be true. It's always false. If it's a truth table, this is a contradiction. If you look in these proofs by contradiction, this is kind of where the form that a contradiction takes. And you will assume P is true, and then using your other assumptions, you'll also show that the negation of P is true. So then you have the statement, well, P and not P. That's a contradiction. So there must have been something wrong, and it's usually the original assumption that was wrong. Question?
So we basically manipulate our statements to end up in the form P and not P.
Yeah, I mean, it's that if you want to break it down to symbolic logic, that's essentially what you're going to get. Like you'll have a statement. I'll give you some problems where you'll show that like x is even, and then some other assumptions, and then you'll conclude that x is odd. So then you say, okay, well x is even and x is odd. That can't happen. That's a contradiction. Therefore, the first line of our proof, where we assume something, our assumption must have been wrong. Okay, so that's the way it goes. So this is a contradiction is something like this. So for this method, we begin by assuming that the statement we want to prove is actually false. Okay? We want to actually start with assuming the statement we want to prove is false. And we'll show that this leads to a clear contradiction. If we use correct logic from that point on, we'll arrive at a contradiction, a statement that can never be true. So therefore, our original assumption was wrong. So if your original assumption was that it's false and that's wrong, then you can conclude that the statement is actually true. Okay. All right. So we begin by assuming that the statement we want to prove is false. Okay. Then we show that this assumption leads to a clearly false statement a contradiction. Okay. Therefore, our original assumption must have been wrong. Okay. So the statement must be true. Okay. So that's to kind of summarize the technique of proof by contradiction. Start with your assuming your statement is false. Show that this leads to a contradiction. Therefore, your original assumption was wrong, and therefore the statement is true. Okay, so we're going to do some examples. Any questions so far? So, proof by contradiction is kind of it's a different flavor often than other proofs we've done. And a direct proof, I had a professor who used to say a direct proof is kind of like a follow your nose proof. Basically, you just keep going forward, just keep following your nose, and you go boom, 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 boom. It's like it's clear what path to take, and especially some of the direct proofs we've written, you just assume P, unravel the definition, therefore this, and then you're done. But proof by contradiction, it can be hard to see where the contradiction is going to come. Okay, and so some of the proofs I'm going to show you, it's not obvious like how to proceed when you have a proof by contradiction. Like to prove that there's infinitely many primes, the proof is not going to be like, oh, that's obviously how I would do it. I mean, it's how everybody would do it, so just keep that in mind. I'm going to show you a couple of classic proofs, but these aren't necessarily stuff the level I want us to be able to prove. These are advanced number theory type proofs. Come on here. All right, here we go. So let's do a proof by contradiction. What do we do first? Okay, I'll do a just more basic result first. Okay, so let A be a real number. Prove that prove that if A is positive, A is greater than 0, then 1 over A is greater than 0. Okay, do you believe that's true? Okay, it is true. Okay. Now, just like when we did proof by contrapositive, you kind of like tip off the reader, like, hey, we're doing a proof by contrapositive here. That's why I'm writing this next phrase. Okay. Oftentimes, you could even write for proof by contrapositive, assume, if it was proof by contrapositive, you would say, well, assume 1 over A is less than or equal to 0, and then you can, you finish when A is less than or equal to 0. But we're going to prove this by contradiction, and so you do the same thing. You let the reader know what's coming. Okay. So often you see this phrase, well, let's start off with our A is a real number. So suppose A is a real number. Okay. Now for a direct proof, I would just say assume A is greater than 0, and then I would kind of work forward. Okay. But what I'm going to do, I'm going to assume this is a false statement. So think about that. I'm going to assume that this is a false statement. So I'm going to write this phrase here. So for the sake of contradiction, so this is the phrase where you kind of let the reader know what's about to happen here. Okay, this is proof by contradiction. Okay, so for the sake of contradiction, I'm going to assume this statement is false. Assume, and I'm kind of maybe write some more words than I would if it was we've done several of these proofs before. So for the sake of contradiction, I'm going to assume this is a false statement. Assume this statement is false.
Is that different or the same as assuming that negation of the statement is true?
Yeah, it's the same. It's saying we're assuming that the negation of the statement is true. That's the same saying that the statement is false. And that's exactly the idea. If I negate this statement, we did this. I'll write this up more precisely later. But if you have a conditional statement, P implies Q, remember what form, what statement is equivalent to the negation of P implies Q? Well, if P implies Q is not true, then P and not Q must be true. So the negation of P implies Q is equivalent, logically equivalent to P and not Q. Okay? So we're going to use that here. So if I assume the statement is false, then I'm assuming there's a real number that is positive and 1 over A is not positive. Or in other words, less than or equal to 0. Okay, so that's my original assumption here. And we're going to show that leads to a contradiction. Okay? Alright. So then there is a real number A with A greater than 0 and at the same time 1 over A less than or equal to 0. Okay? That's my P and not Q. That's equivalent to the negation of the statement. Okay, any questions so far? Here's where my contradiction is going to be. I'm going to use this inequality right here. If 1 over A is less than or equal to 0, if I multiply both sides of an inequality by a positive number, and I have a positive number, A, let's see what happens. So oftentimes with these proofs, you can't, like I said, you can't do a direct proof because it's not like very clear what's going to happen. Sometimes you have to do scratch work. You have to just kind of play around with what you know and what you're assuming, and until you can figure out an equation or some kind of statement that's a contradiction. Okay? So if I'm looking at this, I kind of say to myself, well, what if I multiply both sides of this equation by A? Do you see how that would give me a contradiction? So let's do that. So by multiplying the second inequality by A on both sides, to obtain, well, what is it going to look like? If I multiply both sides of this by A, you'll get 1 is less than or equal to 0. And I can even do, I mean, to be very clear, I can even write it out maybe in more than one step. So A times 1 over A is less than or equal to A times 0. Right? I multiply both sides by A. So 1 is less than or equal to 0.
Break them up into 2 cases.
Well, no, I mean, hopefully you at this point something, you know something, right, that's unsettling. Surely we all know that 1 is not less than or equal to 0, right? So that's the contradiction. This is a contradiction. Why is it a contradiction? Because 1 is not less than or equal to 0, because 1 is actually greater than 0. So remember I told you there's this form of contradictions, the P and not P. So these two statements are negatives of each other. We're saying that 1 is less than or equal to 0, but we also know that 1 is greater than 0. Those both can't be true. It's just like P and not P. They both can't be true at the same time. So this is a contradiction. Therefore, okay, so we made an assumption. Then using correct logic, this produces a contradiction. Therefore, the only thing that could be wrong was our original assumption. Our original assumption that the statement is false. Okay? So therefore, our original assumption is wrong.
So we can't just write therefore 1
And-
is greater than 0.
Well, you can say, you can say that. You can restate the whole sentence. Oftentimes you just stop when you say this is a contradiction. You can just usually just end it. But this is our first proof by contradiction. So therefore, our original assumption is wrong, and the statement is true. So I could say, well, therefore, if a is greater than 0, then 1 over a is greater than 0. But usually, once you state there's a contradiction, then you're done. I could have just put it, a box. This is a contradiction. We get 1 that's greater than 0. Box. Okay. So I just want to kind of complete the thought, the whole process of proof by contradiction. You make an assumption, that leads to a contradiction, so therefore your assumption was wrong. Okay. Any questions so far? So keep in mind, this statement, there's not really any definition. I didn't really define what it means to be greater than 0. I'm just assuming you guys know what greater than 0 means. But the type of proof that you're going to do by contradiction are going to use our basic knowledge math, like greater than 0 or positive or negative, or our definitions, like even, odd, divides, so on. Okay? So I'm not going to make you guys do proofs about infinitude of primes or something like that. So, but that's there is one statement though that is kind of a classic proof by contradiction. So that's the next proof I want to show you. And hopefully by seeing this proof, it'll help you with a homework problem that's similar. Well, we're kind of at a break point, right? Let's take a 2-3 minute break, and we'll see the proof that square root of 2 is irrational.
Yeah, you said that you'd be all right.
Did you never ask me if I was going to be anyway? I didn't. Yeah, you said
So now, homework,
Oh, no, I didn't know you sent an email about homework. I wrote them off for it.
Yeah. I signed it during class too, though.
Yeah.
Right. Oh.
Yeah.
Yeah, she did.
So kind of pounds.
Really.
Okay.
Wednesday last week.
Yeah. So, I thought that I realized that last night. I know I wrote something about chapter 5, and then I didn't put the. Yeah, shoot me an email or something there.
Okay.
For somebody else in class. Especially when you.
It was like 4, 6, 7, 11. And I don't see it.
Definitely remember.
We had that same class.
Yeah, so I wrote the songs on the board too. And posted it on Blackboard.
Oh, yeah.
But I just put it in my book for you.
false. You have shown the number for A, and shown the number as a number. Show that one.
You have to show for all possible numbers. Show the. I mean, that's a, we're thinking of it as a, it's a counterexample.
Yeah, that's what
We'll do, yeah, we'll disprove statements using counterexamples. So that's often how you would disprove something like that. And that's the way I do it, like on a homework. If someone makes a false statement on a homework problem or definition, I'll say, you know, there's a counterexample that shows that your evidence is false.
This logic works on everyday statements too. If you read that, I love to get my wife on that. So mad.
Yeah. Well, if you use the mathematical definition of a word, that drives people nuts, you know.
Yeah.
One or the other or both. Is that 2 minutes? I didn't lose my one. I said 2 minutes. Alright. So let's see. Let's talk about this proof. Square root of 2 is irrational. You believe it's irrational? So you may have seen this with calculators and things like this. You see square root of 2 often in like a calculus class with like trig functions and things. But square root of 2 and any irrational number, you look at the decimal expansion, you know, what do you see? Well, that's with an irrational number.
It goes on.
Keeps going on and on, never stops, never repeats. So that is true. And if the decimal representation of a number started repeating, if there's a clear pattern of repetition, or if it just terminates, then you could write it as a fraction of integers. There's a clear way to do that. So we got to think back. What does it mean? What is our definition of rational and irrational, right? So we call x is irrational if and only if x equals a over b for some integers a and b. Right? That's what it means to be a rational number. Means that you can write it as a fraction of integers. Right? So I'm claiming that square root of 2, you can't do this. You cannot write square root of 2 as the quotient of integers. So I mean that's what it means to be an irrational number. I mean you can define an irrational number as a number that's not a real number that's not rational. But you know, you can say x is irrational. X is irrational if and only if x does not equal a over b for all integers a and b. And you cannot find, we consider all possible integers, you can never write x as a over b. Okay? So this is kind of, think like the proof by contrapositive. When you have these negative statements to work with, like you're going to just kind of prove that square root of 2 is irrational, and you can't sit here and take every possible combination of integer and show that they never equal x. I mean, you can't really work with this negative definition that, you know, x does not equal a over b.
So basically, either A or B has to or be an element of the integers.
Sorry, a or b doesn't matter. Well, I mean, if I'm saying that irrational is essentially saying it's not rational, then that's what it would be. If you're not rational, then the negation of this statement is x does not equal a over b for all integers a and b. So what I'm going to do is, this is a classic proof by contradiction, because if you're going to assume that your given statement is false, then what would that look like? If I say square root of 2 is not irrational, then I'm claiming it's rational. If I'm claiming it's rational, then I have a clear kind of next step, kind of definition to unravel. So that's where we're going to get our contradiction. We're going to write square root of 2 as a fraction of integers and show that I just can't. It just isn't going to work out. Okay, we're going to get contradiction. All right. Any questions about definitions? Just recall those. I don't think that wasn't one of the definitions I gave you on your sheet of paper, right? But you should know what it means to be rational around. Okay. So, proof. So, for the sake of contradiction, suppose that this statement is false. Suppose square root of 2 is not irrational, and it'll be completely normal if you just wrote suppose square root of 2 is rational. Okay, then square root of 2 is rational. But we know what that means. If I claim that square root of 2 is rational, then I can write it as a over b for some integers, a and b. So therefore, square root of 2 equals a over b for some integers a and b. Okay? Any questions so far? Okay. All right. Now, there's kind of a further assumption we need here. Anytime you have a fraction of integers, I mean, if you have a rational number, there's actually an infinite number of ways to write it as a fraction of integers. Right? Like 3, you could write that as 3 over 1. Or you could write it as 6 over 2. Or any, just multiply the numerator and denominator by any other integer. You write it as negative 6 over negative 2. So there's an infinite number of ways to show that 3 is rational. I mean, you only need one. It just says for some. At least you can find at least one pair of integers that whose fraction equals that given integer. So clearly 3 is rational. But what we're going to do, so these fractions, these are not reduced fractions. These are not simplified fractions because they have the numerator and denominator have a common factor. So it's really not an unreasonable assumption. I mean, we're not losing any generality by assuming that our fraction is reduced. Okay? So we're going to need that. We're going to assume that this fraction a over b is a reduced fraction. Okay? You buy that? That sounds reasonable? I mean, because if it's not, just cancel any common factors. I mean, so if this isn't a simplified fraction, you could just cancel common factors. And you would eventually get a reduced fraction. So that's what we're going to do. I'm just going to assume that a and b are reduced fraction. Is a reduced fraction. A over b is a reduced fraction. All right. So further assume that this fraction is fully reduced. So what that gets us is that if it's fully reduced, there's no common factors of a and b. A and b have no common factors. If they had common factors, then you would have canceled them. Okay, 7.
So do we have to put the without loss of generality?
You could if you want to, but and so to kind of justify that, I'm going to even write a little phrase inside parentheses. So further assume this fraction is fully reduced, and you kind of think to yourself, well, yeah, can you do that? Is that really without loss of generality? So if it's not reduced, just cancel any common factors. that's kind of where, so I'm kind of justifying this assumption. It's really not that big of a deal. If there were common factors, you just cancel common factors. Okay. All right. So we got a fully reduced fraction. Now, what that's going to do for us is we're going to use the fact that they have no common factors. A and B have no common factors. So in particular, they both can't be even. Think about that, right? I mean, if you had a fraction where the numerator and denominator was even, both were even, it can't be reduced, right? Because if it can't be a reduced fraction because there's a common factor of 2, you could cancel. So there's no way that A and B can both be even.
Or B divides A.
We're not talking about division here, but that's where we're going with this. So you might not see the big picture right now, but where am I going to get a contradiction? So here's kind of the bigger picture. I'm going to assume that this is a fully reduced fraction, so A and B are both not even. When I square both sides of this equation, we'll get a factor of 2 on this side, and then there's going to be a factor of 2 on this side, and we're gonna have mismatched factors of 2, and that's where we're going to get a contradiction. Okay, so we'll see, that's where we're going. Okay, but any questions so far? So we assume fraction is fully reduced. We're pretty good so far. All right. So then, as I said, then A and B are not both even. Ever see why? Because if they were both even, then the fraction is not reduced. Okay. So otherwise, the fraction A over B is not reduced. Okay. Let's square both sides of this equation. Squaring both sides of the equation gives, well, when you square the square root of 2, you would just get 2. Okay? So 2 equals, and then square the right side, I can square the numerator and denominator, and I get a squared over b squared. Okay? Any questions about that? So square both sides of the equation. You get 2 equals a squared over b squared. So if I multiply both sides by b squared, I get the equation a squared is going to equal 2b squared. Okay? All right. Well, what can you tell me about a squared now from this equation? It looks like 2 times an integer. This looks like a homework problem or something. You have something similar to this, right? So if a squared equals 2 times an integer, then we know that a squared is even. Right? And a squared is even. And if I know that a squared is even, what does that tell me about a? Can I assume that a is even? Is that obvious? If a squared is even, then a is even?
Didn't we prove that?
We did. We proved that in class. We actually proved that in class. So then a squared is even. Okay. So we proved in class. So you don't have to take my word for it. We just look back at your notes. We actually proved this statement. We proved in class that a squared is even implies a is even. Right? We actually proved that in class. I think it was, I don't remember if it was proved by positive, but we did prove that if a squared is even, then a is even.
I think we did it if A is even, then A squared is also even.
I think we actually did this. This is even a more useful, more powerful statement. I mean, if a squared is even, then a is even. And I look back at my notes, and we did prove that statement in class. Okay. All right. So,
A is even and A is odd.
well, if a is even, then can b be even? No. Remember, we said they both can't be even. But we have a is even, so what do we know for sure now about b? B is odd. Okay? Then b must be odd. Yeah, that's right. Okay, remember why we said that? We said that here, right there. They can't both be even. Otherwise, a over b is not reduced fraction. If we say a is even, then we can conclude that b is odd. Okay, good. All right, now, since a is even, how can I rewrite a? Since a is even, a equals, let's say, 2c for some integer c. Right? I know a is even, so a is 2c. Now I'm going to replace this a here in this equation with 2c. Okay? Then 2c, the quantity squared, equals 2b squared. Okay? Let's multiply this out. So 4c squared equals 2b squared. I've got a common factor 2. I can divide both sides by 2.
2c squared equals b squared.
Let's say so 4c squared equals 2b squared, b squared, and 2c squared equals b squared. Well, what can I conclude about b? B squared is even, and then therefore b is even. So then b squared is even. And therefore, b is even. Anybody see a contradiction? Yeah, we have two statements. B is odd and B is even. This is a contradiction. This is a contradiction. You can just kind of end it there, or you could say, therefore our original assumption was wrong, therefore square root of 2 is irrational. Okay. So it's kind of a classic proof by contradiction, square root of 2 is irrational. And then a similar proof could be written for any square root of like a prime number, for example, like square root of 3 is irrational, or
Well, pi.
Pi is irrational. Well, I don't think you can use the same type of proof. I mean, it's actually harder. Pi is not just irrational. Pi is transcendental, which is it's just so you can't use exactly the same type of proof. But so the benefit here is that if I square both sides, now I have integers. So now we have all integers, and then so that's where we can use our even and oddness. Because every integer is either even or odd. Okay. But you square, if you have pi equals a over b, it's not going to be exactly clear what to do to get a contradiction. Okay. But you could use the same proof, similar proof to show, like, for example, square root of 3 is irrational. If you have, well, there'll be some differences, but it's kind of the same thing. You write square root of 3 as a fraction, and then show that leads to some kind of contradiction. So, all right. Any questions about this proof?
So you can look for any contradiction anywhere. Just you get one, you're done.
Yeah. I mean, because I assume that square root of 2 is irrational. That probably would not you would not guess off the top of your head. Okay, that shows that B is. Then we're going to use the contradiction B is odd and B is even. And it doesn't. It's not clear. It's not direct like a direct proof would be very clear like what's the next step going to be. You can get any type of contradiction, and that'll. This is why our proof like this is beyond the scope of this class. I mean, this is really. I mean, to come up with this on your own. Okay, I mean, you can kind of mimic this kind of proof, and we give you one problem that's you're going to kind of mimic this proof for homework. Okay, any questions? Any more questions? That time for another big theorem. You believe that there's infinitely many primes? Yes. You do? Prove it. So that means we have to prove it. So we all agree, and we don't have to prove it? Sure. Yeah. Most mathematicians would believe that the Riemann hypothesis is true, but we don't have to prove it yet.
Yeah.
All right. Big theorem.
Yeah.
There are infinitely many primes. Okay, this is basically the same proof that Euclid gave thousands of years ago, 30,000 years ago. So, proof. For the sake of contradiction, what would you write next? Sure. Anything that's equivalent to the negation of the statement, right? Suppose there are not infinitely many primes, which is saying, suppose there are finitely many primes. Okay, for the sake of contradiction, suppose there are only finitely many prime numbers. Okay. I mean, if you want to get nitpicky, you could say something. You would say, suppose there are not infinitely many primes. That's the same saying. There's finitely many. Okay. So finitely many means there's like 1,000 or there's 2,000 or whatever. There's some fixed number of primes. These are the only ones. I mean, you could actually, there might be a lot, but you could sit there and write them all out. Okay? Well, what I'm going to do is assume, let's actually have some symbols to stand for all the prime numbers. Okay? So, suppose that there are n primes. So suppose there are only finitely many primes. Say there are n prime numbers. Those are n prime. Okay? All right, let's list them out, and I'm going to kind of, some notation here. So let P1, comma, P2, comma, P3, comma, all the way up to Pn. Be a list of all the primes. Okay. All right. Any questions so far? So suppose there's n of them. I mean, n can be a really, really big number. We don't know, but suppose there. Okay, here they are. P1 through Pn. Okay. So what would the first prime? If I list them in order, P1 would be 2, it would be 3, 5, so on. I mean, and then we have Pn's the last one, the biggest one, I guess. Okay, we don't need to know that they're in order like that, but here's what we're going to do. We're going to get we're going to build. We're going to combine these some way. So consider the number, call it m, which equals, what I'm going to do, I'm going to take all these prime numbers, I'm going to multiply them together. Okay? So P1 times P2 times P3 times all the way up to Pn. Okay, I'm going to multiply all the primes together, and then I'm going to add 1 plus 1. Okay? Everybody understand the notation? So I take all the prime numbers, multiply them together, and then add 1. Okay? So, I mean, there's a little bit of maybe a little bit of stuff I'm going to assume that I haven't proven, but let's look at this number. So this is this clear that this has to be a natural number? I mean, every one of the prime numbers are natural numbers. You add 1 to it, you get another natural number. Okay? So natural numbers are closed under addition. So then m is a natural number. And therefore, m has at least one prime divisor. Do you believe that statement? I mean, every natural number has at least one prime divisor. I'm not really proving that, but I mean, would you buy that statement? Okay, how much? So this is true. I mean, this is true. Every natural number, I mean, fundamental theorem of arithmetic, you know, you can write every prime number as a, you can write every natural number as a unique product of primes. That's where I'm not really proving this statement. Okay. Okay. If you grant that statement, then we can continue. So m is a natural number. Okay, and therefore m has at least one prime divisor. But these are the only ones. These are the only candidates. Right? These are the only prime numbers. Right. So one of these guys has to divide m. You see where we're going to get a problem? If some prime number goes into m, divided into m equally or evenly, then we can divide this and it'll divide into this stuff. I mean that same prime number is here, but it's also going to have to divide the number 1. So that's where we're going to get a contradiction. Okay, so then m is a natural number, and therefore m has at least one prime divisor. Let's say p sub k divides m. Okay, there's one of these guys. I'm going to call it p sub k. All right. Well, if p sub k divides m, then m looks like p sub k times c for some integer c. But let me replace m. So then p1 times p2 times p3 times all the way up to times pn plus 1 equals pk times c. I'm going to divide both sides by pk. So dividing both sides by p sub k gives, well, imagine I divide this both sides by p sub k. The p sub k is going to cancel on the right side. I'll be left with c. Here, when I divide this by p sub k, it's going to cancel. This p sub k is somewhere in this product, so I'm going to cancel that p sub k, and then I'm going to get 1 over p sub k. Okay, so that's my next step. Okay, So dividing both sides by piece of k gives P1, P2 times P2 times P3, all the way up to Pk minus 1 times Pk plus 1 times P sub n. Okay, so I've shown, I'm taking out the factor Pk, piece of k. I got the prime before it and the prime after it, but Pk is gone now. Plus 1 over piece of k equals c. Okay. Now let's think about this. This stuff over here equals c. What did I know about c? What did I assume about c?
It's an integer.
C is an integer. Does this look like an integer to you? And this stuff's an integer, but the plus 1 over pk, that's not an integer. So that's where the contradiction is coming. So you'll see here, so I'm going to write this up. So then 1 over piece of k equals c minus p1 times p2 times p3 times pk minus 1 times pk plus 1 times p sub n. Is an integer, which is an integer. So c is an integer. I'm subtracting a natural number, a product of natural numbers. So this right hand side clearly is an integer, right? So 1 over piece of k is an integer. That's a contradiction. Why can 1 over piece of k not be an integer?
Because 1 is a prime.
Yeah. I mean, yeah. If you think about it, if every prime number, we know every prime number is bigger than 1, right? So a 1 divided by a number that's not bigger than 1, it can't be an integer. Okay. So 1 over piece of k is an integer. This is a contradiction. So we're done. Therefore, our original assumption was wrong. We assumed there was only finitely many primes, so that led to a contradiction. Therefore, there are infinitely many primes. Now, I mean, I thought about adding some more here. Is everybody truly convinced that 1 over pk is not, can't be an integer? I mean, if you said this was an integer, then the only way that would be an integer, could be an integer, pk would have to be would equal 1 or negative 1. But neither of those are prime numbers. Right? I mean, if I said 1 over pk is an integer, that would force pk to be equal to 1 or negative 1. Those are the only two integers that divide 1. But 1 and negative 1, neither of those are integers, or neither of those are prime numbers, I think. So you could maybe write a little bit more, but I think people be convinced that that's a contradiction. Okay. So this is essentially the same proof that ancient Greeks came up with at least 2,000 years ago.
So it'd be like something where we would end up dividing by 0 and then sometime we would see the proof by contradiction.
Sorry?
Or getting to a situation where you divide by 0, would that be another situation? You'd see proof by contradiction.
Well, yeah, I can see you can do proofs like that where you say sum doesn't equal 0, and then you can divide by it, and then you show that it leads to some other contradiction. Yeah, it's kind of strange. I mean, so these proofs by contradiction, it takes some scratch work. It kind of takes a lot of thinking before you can, for these complicated proofs, before you can actually come up with these types of arguments on your own. Now, the ones I'm going to assign should be more kind of direct. They're really going to be if-then statements. Okay, so this is actually section 10 minutes here. Look, just real quick, let me talk about how do you prove P implies Q by contradiction. So I did one of these statements already. I briefly mentioned this. I'm going to be more give you more details. Okay. So to prove P implies Q, by contradiction, we start by assuming the negation of P implies Q is true. But we have shown that the negation of P implies Q equals P and not Q. So when you start off proving a conditional statement by contradiction, your first sentence is going to be this. Assume P and not Q. Okay? So thus, our first step will be to assume P and not Q. Okay. Give me one quick example. I did one statement like this. Let me do one more real quick. I didn't move my camera over there, did I? I wanted to be over here anyways. Okay, so second on the board. Let's you participating at home. Alright. You can hit the pause button. Alright, let's move on. So let's do an example. I'm trying to rush here. Why is everything so down when you're trying to rush? Notice. Alright. Let A, B be integers. Prove if A minus B is odd, then A plus B is, what do you think? If A minus B is odd, then A plus B is odd. Oh, so this is not an obvious statement?
Okay.
Huh. Good. I'm glad I showed this. It's actually odd. Yeah. Let me prove it. Okay, so proof. For the sake of contradiction, what? Assume what? A minus B is odd, P, and not Q.
A plus B.
Okay? For sake of contradiction, assume A minus B is odd, and A plus B is not odd, but I'm just going to say again. Or I'm out of time. Alright, so that's P and not Q. Any question? P and not Q. That's equivalent to the negation of this statement. Alright. Then, okay, if A plus B is even, then A plus B looks like 2 times an integer, right? So since A plus B is even, then A plus B equals 2C for some integer C. Now, however you want to write A minus B equals 2 times an integer plus 1. We don't need that. What I'm going to show you is that if I assume that A plus B is even, now it's going to show that I'm going to prove to you that A minus B has to be even as well. and that's where I'm going to get my contradiction. We've already assumed that A minus B is odd. All right, here's a little trick. This happens. This is a trick. We'll see time to time in proofs. Mathematicians, when they're dealing with equations, sometimes you might want to have a different form. So what they'll do is they'll add a term that they want and then subtract it in the same equation. You ever seen this trick before? So I want it to look like A plus B. Okay? But if I add a B, I better subtract a B. Okay? So think about this. What changed from A minus B here? So I have an A and I have a minus B. I added B and I subtracted B. So this is a common trick. Right? Like these two cancel out, and what do you get? You just get A minus B. Right? Alright. So this, I like that. Alright? That's A plus B. Minus B is minus 2B. You see why this has to be even now? We'll kind of replace A plus B with 2C. This equals 2C minus 2B, which equals 2 times C minus B. Thus, A minus B is even contradiction. I assumed A minus B was odd, and A plus B is even, and I just showed that A minus B equals 2 times an integer. Therefore, A minus B is even. I left out a little bit of words. You might have another sentence that says, then A minus B equals 2D for some integer D, which equals C minus B. Thus, A minus B is even.
So we know A minus B and A plus B have now the same clarity.
Is that true? Maybe that's not what I said. But maybe it's true. They're saying it. And that's a good quiz problem. You have to do that by cases. All right. So we'll wrap up there. So we had a quiz Wednesday on the direct proof stuff. Oh, I didn't give you your homework.